Okay, so we look at the final section in chapter 1, which is 1.5, the book roadmap, and I like to illustrate the book roadmap by a packet slide. Okay, so we like to see how a packet traverses within a router and within a server. And then there's a sidebar in the text telling the story from the birth of a packet at a client and passing through the many routers and then eventually reach the server. So there's a sidebar describing the process. But here, we focus on, we want to zoom in to see the operation within a server and the router. Before that, let's look at what the packets look like in Linux kernel. Within Linux kernel, there's a structure called skbuff. Okay, it is a structure to point to the actual space that store the packets. So here, in this figure, you see there are 3 skbuff structures, and they are linked together by double linked list. So we got 3 skbuff here, and they are linked together by the double linked list. And then there's a series of header pointers point to a space that actually store the packets. So the packet is actually stored here and pointed by the pointer within the skbuff structure, header and the payload. So I have, say, the MAC header is here, and then the IP header is start from here. So I have MAC header and IP header here, MAC header and IP header here, and then the transport header here, and then application header and payload start from here. Okay. And if you look at this packet, you see that the MAC header is here, the same. However, there's another pointer point to here to the IP header, meaning okay, what data I'm processing right now. So this pointer can indicate what address I'm processing right now. So perhaps I have finished processing the MAC header. And next, I'm going to put IP header. So I point my data pointer here. Okay, and the structure, the space might not be filled because the packet length. Okay, the packet end here, so I have some empty space. Okay, so these are the structure that is used. This is the structure used to store packets, the actual packets. And you will see that, you can see that the packet within the kernel, it's all stored in this manner. And the packet will join to different queues. So actually you don't, then one question you might ask, why do I need to separate the structure and the packet? Why do I need to separate this? Why not put this into this structure? First of all, the packet length is variable, it's not fixed. So it's not good to put into a fixed structure. And secondly, the packet might join different queues. And when they move from one queue to another queue, I don't want to do what? I don't want to do memory copy. I don't want to copy the packet from this queue to another queue. I just need to change the pointer here. I just need to change the pointer here to join, so that the packet will join another queue. Right? So you can see, so I don't need to copy the packet. I don't need to actually copy the packet. I just change the pointer to join different queues. Okay. So you can consider the skbuff structure is the metadata of the packet, while the actual data of the packet is in another space. that will be pointed by several pointers within the escape buff. And when you have a new packet coming in, you need to allocate, allocate another escape buff structure and also the packet space. Yeah. And actually, there's a pool of structure, escape buff structure, so that you can grab a pool of idle escape buff, so that you can pull to get the structure when there's a new packet. And when the packet leave the system, the Linux system, the escape buff the structure will be released. I mean, the structure for that packet will be released, and then put it into the pool of escape buff. Okay, so as I said, there's a pool of escape buff structure here that set idle, and when you have a packet coming in, you grab one from this pool. So next, let's look at with a web server, how does packet traverse within the kernel? Okay, suppose this is a web server, and it has one interface call. So the packet come in, and the NIC call, network interface call, receive the packet, and then it would generate interrupt, as we mentioned, as we illustrated. It will generate interrupt, and then the CPU control will be passed through the driver, the transmit module within the driver. The receive module within the driver when there's a packet coming in, and then this receive module will then get a space from the escape buff pool, and then so that it would put the structure, the packet into the queue. The packet will then join the queue here, waiting to be processed. So there's a queue here, and then once put into the queue, the driver has done its job and finished. And then it's the IP layer's job to grab the queue. Once it has the chance to execute on the CPU, it will grab the packet within the queue, okay, to do the processing. See, it would check several fields within IP headers, and then check IP table. I mean some filtering table here, and then pass. This is packet A, which is a request. Say packet A stands for the user request, meaning HTTP request from the client to the server. So I'm passing the request up, and then within TCP, the packet would trigger congestion control and error control, and then all the way to the receive module here, and then there'll be a acknowledgement packet sent back to the client. So here the server would, within the TCP, the server would send an acknowledgement back to the client. So there is a packet B, which is a TCP-ACK for packet A. And then the request will then come to the socket layer, and because I need to copy the request to the web server, the daemon, which is in the user space. So my request need to be copied from the kernel space to the user space. So all the way here you are within the kernel space, but now you need to cross the boundary, cross the kernel and user space boundary, and copy it to the user space memory. And then the daemon will process the request here, and then prepare the response, and then send the response down. So it would issue. So the client, the server here will call the read operation, the read system call, to get a request. And before the request comes in, the read system call will block. It'll be waiting there until the request is actually copied to the user space. Then the read system call will return. And here, you write the response down to the kernel. And then again, the response will need to cross the boundary from the user space to the kernel space. So that will be package C, the web response, to the response to the request. So the package C will go down and then into the kernel, and then passing through the error control and congestion control, and then IP layer, and add the IP layer and calculate the checksum, and then pass through the driver. And then there's a queue within the driver, which is a transmit queue, and waiting here for the driver to process. Again, when it's the first packet of the queue, it would trigger the driver to program the NIC card. It would trigger the driver to program the NIC card immediately. So the driver will then issue command to the register on the NIC card, as we mentioned. Okay, and then it's done. Okay, once the NIC card, well, we say that the NIC card will do the DMA to copy the packet from the main memory to the NIC card memory. And once DMA has done the job, then the NIC card will transmit the packet to the network. And once it finishes the transmission successfully, it will interrupt the driver, interrupt the CPU, and the driver gain the control again. And then the driver will know that, okay, the packet has been transmitted successfully. And if the driver has more packet in the queue, it would issue command again. So this is the process. And here, the client then receives the response. And the client TCP module needs to send the acknowledgement back. So there's a packet D, TCP-ACK, returned from the client for packet C. Okay, so you got D, packet D coming in here, and then in here, and then here. So, and then end here. Okay. So these are the process involving 4 packets, okay, for client server request and response, and because request and response each will trigger an ACK because they run on TCP, and the ACK will be sent by the TCP layer. So they are totally 4 packets. And here we, throughout this process, we cover different things in different chapters. In chapter 2 and chapter 3, we cover the NIC layer. The NIC, the hardware, and also the driver. So this is the hardware. The NIC card is covered in chapter 2 and chapter 3. The driver is also covered in chapter 3. There's a section within chapter 3 covering how to write the drivers, or how the driver works, and illustrate the detail of the driver operation. And I just mentioned the rough procedure within the driver. Okay, so chapter 3 cover up to here, and then the IP layer here will be covered by chapter 4. And the TCP or transport layer will be covered in chapter 5. And then chapter 6 will cover the application layer. Okay. Then why we didn't see the chapter 7 and 8, chapter 7 and chapter 8? Because chapter 7 and chapter 8 are two advanced topics on QoS, quality of service, and also on security. And it's not covered or implemented or supported in a web server, so it's not in the picture here. However, in the next page for the router, you will see chapter 7 here. It does some traffic control. You could put some traffic control within the kernel, and that's covered in chapter 7. And here, you might have a intrusion detection module or intrusion detection daemon here. Say snort is a daemon, an intrusion detection daemon, and that is covered in chapter 8. So, but before that, let's continue to see a packet line in a router. Here, in a router, it has at least 2 interface cards, 2 NIC cards. You need to have at least 2 in order to be a router, or maybe you have more interface, say 12 or even more. Okay, and there's a packet coming in here. Suppose there's a packet, well, here we got 2 interface cards, and each of them has transmit and receive within the driver. Suppose a packet comes in from into this NIC card, and then it would interrupt the CPU, and the driver would take the control of the CPU, and then it would put the packet into a queue. Okay, and the TCP module will get the packets from the queue and then do the check, just like within the server. And then here you need to do some filtering job, perhaps some proxy or some classification, flow classification. And then you would come to here to do the routing decision. So the packet might be, say, if I'm a router, most of the packet will be here, will go this way, and then this. This. We'll go this, and then go out. See, because most of the packet will be transit packet. By transit, I mean the source IP address and destination IP address are not this router, do not belong to this router. So all the packet have most of the packet will be transit packet. Then I will go this way and do the check here on the forwarding chain and NAT here. This is actually NAT, and then traffic control. Okay, maybe multiple queues, and then to the driver. But some of the packet will not be transit. Say, if I have a routing message from another router, then the packet is destined to this router. Actually, it's destined to the routing daemon here. So the packet will be forwarded here to here. The destination IP address is local, meaning destined to this router. Then it will be passed here and then passed to the routing daemon. And again, here you need to cross the boundary from the kernel space to the user space. So the if this is a routing message, then it will pass to the routing daemon, say Zebra. Zebra is a routing daemon. It does the calculation to find the shortest path. Then you do the calculation here. Okay. And again, the Zebra daemon can receive routing message from the other routers. Okay. It would also send routing message to the other router too. So So it would say the source IP address is local, meaning the packet is sent by Zebra, the routing daemon. So it will go down this way, and then here, and then here. Okay. So if it's a routing message going out or outgoing routing message, it will go this way, and then this. Okay. So if again, let me summarize. So 3 possibilities: transit traffic, transit packet, which account most of the packet process. And the source and destination are not this router. So the packet will go this way, and then this, and do the checking here, and do the NAT here, and then traffic control, if any, and then to the driver, and then send. That's the majority. And if we have incoming routing message, then it will go this way, this, and then to the routing daemon. And if we have outgoing routing message from the routing daemon, it will go this way, and then this. Okay, so these are the 3 possible flows. And similar to the server, we cover, well, we have said that the NIC card, the hardware, the transmission, reception, the physical layer, and also the link layer are covered in chapter 2 and chapter 3. And the driver is in chapter 3. And the whole IP layer in chapter 4. And usually within the router, you probably don't support transport protocol, probably only for the daemon. So you don't see chapter 5 here. Chapter 5 is on the transport layer, so you don't see chapter 5 here. And you don't see chapter 6 here. Chapter 6 is on application layers, application layer. So chapter 5 and chapter 6 are not in the picture, because router usually implement up to the IP layer, right? The transport layer is for end-to-end host, for client or the server. But you do see QoS within the kernel and security there for intrusion detection in the daemon. However, security could be implemented in the kernel too. For example, you will see in chapter 8, we have VPN and firewall. And VPN mostly is implemented in the kernel. And firewall, if it's TCP/IP firewall, it will be in the kernel. If it's application firewall, it could be in the daemon. Okay, so we see the package live in a web server and also in a router, and there's a sidebar on describing the story from the birth of a packet at a client, traversing through several routers, and then reach the server. So you can take a look at that sidebar. And there are two other sidebar, performance matters sidebar. And this one, we actually measure, we actually profile the time spent within the server, the time packet spent within the server from socket to driver, excluding the application layer. I mean, excluding the times in processing the request and preparing the response, excluding that. Just look at from the socket layer down to the driver, okay? And you will see that within the server, what dominates? The transport layer rank first. I mean, rank is consumed 26 and 21, so that will be 47%. So 47% are spent on the transport layer. And then IP layer, 32% totally transmit and receive. Okay, so why there's some explanation in the textbook about why it spend more time. That's because one is the TCP handling. The TCP handling consumes some time, and also another will be the interrupt and memory copy between the kernel space and the user space. Okay, because at the transport layer, the kernel needs to handle the interrupt. If the application, I mean the daemon, the client or the server call the system call, then there'll be software interrupt. And usually then there'll be a memory copy from the user space to the kernel or vice versa. So interrupt memory copy will be probably the major overhead there. And then next will be the TCP handling will be another overhead. So that tells why the transport layer accounts for a dominant factor. And how about a router? Within the router, with the router, we don't see transport layer, right? Because I just mentioned that you implement up to the IP layer, the network layer. So you will see IP layer. Okay, well, it's heavy in reception, but not as heavy in transmitting. The dominant factor will be the link layer. Why? Well, you also see the DMA, but the time on DMA is not the CPU time, not the CPU consumption time. It's the eclipse time, meaning without CPU involvement, but you still need some time to wait wait for the packet being copied inside, incoming or outgoing. But that's not the CPU time. The other will be CPU time. Okay, but why link layer dominant? Okay, that's because the IP layer is light actually, and that's so without transport layer, then the link layer would dominate. And why do we need time for the driver to handle this, the transmission and reception? That's because the driver needs to prepares the header and also deal with the hardware. So the driver would need to spend time on header preparation and also the interaction with the NIC card. So that's the overhead. And if you look at the time you need to pass through the protocol stack, the total time in a server is 34 microseconds. 34 microseconds. I mean round trip, not one way, but round trip. But excluding the application daemon, the application program. So 34 microseconds. Here, it's 29 microseconds within the router. So it's smaller, and because you don't have the transport layer overhead. And actually, when we do the experiments, the hardware platform we use are different. I mean, for the router and the server. For the server, we use a high-end platform, 2 gigahertz CPU. But in the router, we use a low-end PC. It's a 1 gigabit hertz. And even the router use a low-end platform, the total time is still less. So you can see that the overhead for the router without transport layer, then the overhead will be much lower.